to have a recording on. Mia, do you have 2.8 number 4? Yeah, sure. So I am going to open up the PDF, and I'm going to just screen clip this in so that I don't have to try to draw this graph by hand. So just be a sec while I find the page and everything. Okay. All right. So the first thing I'm going to do, Mia, is identify all the places where the derivative would be 0. So those are going to be the extrema, right? The relative maxes and mins. So my function would have, or my derivative would have zeros at those values of x. Cool with that? Then I'm going to look section by section and say, okay, the slope in this section is decreasing, and that slope is, or that function is decreasing in that section, so its slope is negative. So the derivative should be below the y-axis there. And I notice that as I'm getting closer and closer to that minimum, the slope of my function is getting closer and closer to 0 also, so it should be like curving. So I'm just going to have it like curving up to that point. I'll look then at the next section and say, okay, that's increasing, and it starts off relatively small, like the slope at the very beginning of that section isn't very steep. It gets very steep in the middle, and then it starts getting very small again, right? So it's going to look like that or something. And then we'll look at this next section. And there it's decreasing, so it starts off kind of decreasing slowly, so it's a negative slope. And then it starts decreasing fast, and then it starts decreasing slow again, right? So I'm going to have like another similar hump like that underneath the y-axis because the slope there is negative. And then the last section we're increasing, and we start off increasing slowly but then get very steep. So again, positive slope, so it should be above the y-axis, and it should be something like this. Now when Mr. Kulik's checking something like this, what he's looking for is that you have the x-intercepts in the right place, and the graph is above or below the x-axis in the correct places. So I'm not worried about like, how high did you make this? I don't know. You know, like it just needs to be, there needs to be a bump there though, and it needs to be above the x-axis. If you'd drawn it like this, I'd say, okay, you know, like there's no scales on here anyway, so it's not like you can really scale it. You know what I mean? Does that feel good, Mia? Okay. Mackenzie? Same section? Yeah. Sure. This is a sneaky one here, Mackenzie. You picked a good one. All right. So first thing I'm going to look for is places where the derivative is 0. Are there any? The answer is no. Why are there You say there's three extrema, Mr. Kulik.
Oh, are they not connected?
Those are corners. The derivative will fail to exist at all of those points. So whatever my function is doing, it's going to have an open circle at those points, wherever I need to put that open circle at. Everybody's cool with that? Okay. If I look at the first section, the slope there is negative, but that's a straight line, right? What is the slope on a straight line? Constant, right? So that's just going to be some constant negative value. Everybody okay with that? The next section is positive, and that looks a little bit, does that look a little steeper than the previous section? I think so too. So I'm going to start with a open circle, and I'm going to make that distance from the x-axis a little bit higher. I'll draw that section.
So wait, why is not an open circle on the left?
Because this value, the derivative fails to exist, so it needs to be undefined on both ends.
Like, how do you know it's
Oh, I'm just assuming that because the graph doesn't have a solid point at the end, I'm assuming it stops or keeps going forever.
So if I did put a circle there, would that be wrong?
You could ask whether the f of x is going on forever or not,
Okay.
and I would just tell you to clarify that.
Sounds good. If
Since
it
the-
is, just be like,
yeah.
not, then it's
Just a point. Yeah.
This is Sergio.
Hold on here a second, guys. I still have a little bit more to do on this one, but Victoria, did you have a?
I just don't understand how I didn't know I was going to do this.
Oh, so on the previous one, let's say I'm looking at this point, right? If I try to draw the tangent line for that,
Okay.
the tangent line's a horizontal line,
Yeah.
which means its slope is 0, which means the derivative there should be 0. That's what you need?
Yeah, so then for 9, none of them are equal to 0.
Correct.
Because if you do a tangent line, let's say, let's look at the top point.
Because the tangent line from the left would look like this, but the tangent line from the right would look like that. So there is no derivative there. Does that feel okay? Since like the limits would disagree. Okay. We'll do the same thing next for this section. Again, that's negative. So we're going to be down below, but it's steeper than the previous negative section, so I'm just going to draw it a little bit lower. And then the last section is positive. So I'll draw, but it's not as steep as the previous positive section, so I'm just going to draw it like that. So it's not quite as high. Mackenzie, how does that? It's tricky though, right? With all the jump discontinuities all over the place.
I think it's easier than the other one.
Yeah? Good.
Yeah, this is a lot easier.
I have a question.
Okay.
on the other one.
Yeah.
So if your slope is negative,
Mhm.
you're below the x-axis.
Yes.
And if the line is like negative, you're on the left of the y-axis. Like the line, like the yellow and the green highlighted line,
Uh-huh.
those are both to the left of the y-axis.
So you're talking about a point here,
Yeah.
right? Some x comma y. The corresponding point here is the same x, but the y coordinate would be like f prime of x, the slope at that point. So like the slope of the tangent line at that point is a negative value. Is that what you're asking?
Yeah. So, yeah. Okay.
Yeah. Yeah. So again, like, I don't know that I really understood your question, but I think I knew what you're getting at.
You knew.
Okay.
You knew.
I knew. Okay. Mia, 51 from that same section? Sure.
Yeah.
let's do this.
So yes, there'd be a point on the x-axis.
Okay, so it says if a does not equal 0, use equation 2.7.5 to find f prime of a. And just go back and double check what that was. Oh, they want you to use that one? I wouldn't want to use that one, but okay, whatever, I'll follow the directions. Okay. Just as a quick aside, why do you suppose they're disallowing a to be 0?
Oh, because the x is zero.
Read part C.
Oh, okay.
Because the derivative would fail to exist there at 0. So that's why they're saying, that's why that little piece is there. Saying, assuming that a is not 0. Because they're like, we'll get to that in a minute. Everybody feel okay?
Why is it over x?
That's just the formula from equation 27.5.
This isn't like the normal derivative.
That is not the normal derivative formula.
Like the easier one that's less good.
Yes, the easier one that's sometimes less convenient to, or most of often less convenient to use.
The other one's 1 over 8.
Yes, correct.
I'm assuming on the test you'd have us use the other formula.
That would be my assumption. Everybody's okay with what we've done here? All right. Who sees what I want to do to simplify this? What's the conjugate for a cube root, though?
I don't understand that, so I don't know.
Here's the way I would think about this problem. Is I would think about the denominator as a difference of 2 cubes. If I do that, I can factor the denominator using the difference of 2 cubes factoring pattern. Who remembers that? That's the difference of 2 cubes factoring pattern. We did it in Algebra 2. I was your teacher, and I know I did it, so I know that you saw it.
No, I know. But I remember doing it. I just don't remember like. What
I don't.
You didn't have Algebra 2, so. Algebra 2 is probably like the easiest math. It was so easy.
So far, so good, Mia?
Yeah, I just would have never.
Well, again, that's the point of like some of the problems I assign are things like I don't have time to like cover every little trick in the notes, and are things that like I want you to get stuck on and we have to talk about. But it's like would be so overwhelming to try to cram all this down your throats in just the notes that it's better to assign some stuff, let you get stuck. Be like, yeah, this is the trick. Good luck of coming up with that on your own. But now that you've seen it, be like, okay, if I have cube roots in here, maybe I can do something with that. So these pieces can reduce. So far, so good. Now I can now direct substitute this because everything that was going to cause a problem is out of there. And so what do I end up with? 1/3 cube roots of A. Okay. So that was the hard part. Part B, quite easy. In part B, it says, show that f prime of 0 does not exist. Oh, shoot, I forgot the squared on that A, right? A squared. It doesn't matter, right? If you, so let's say the nth root of a to the m is equal to the nth root of a to the m, which is also the same thing as a to the m over n. So you can kind of move those exponents wherever you kind of want to make it convenient. Felt like it was just going to be less confusing to just sneak it under the radical there. Okay, so that's part B. I think that's enough. Part C says then show that y equals x cubed has a vertical tangent line at 0, 0. Okay, so if I'm looking for the slope of the tangent line, I'm looking at like f prime of 0. And what am I expecting this to be if it's vertical? I want the limit to go either positive or negative infinity, right? Undefined, basically. So here you could do either one, but I think that the same setup as we did before is probably going to be preferable. Oops. Is that so far so good? And I guess we could do it from the left or the right also. It doesn't really matter. Well, it says it wants to show that this guy has a vertical tangent line. So that's basically, I'm showing that the slope is going to be undefined. Is it the same thing? Well, here I showed that the slope, I just showed that that doesn't exist, right? That's not in the domain. So we'd say like, therefore, 0 is not in the domain of f inverse. Here we're showing the same thing, but like, it is the same thing because the slope of the tangent line at 0 is the same thing as the derivative at 0. So if the derivative doesn't exist, one of several things could be happening. Among those things is there's a vertical tangent line, but that doesn't have to be what it is. That's why I'm doing the limit here, is to show that like I'm actually going to evaluate this and show that it's not because the limits disagree, it's because it's infinite, right? Because you could have like a jump discontinuity or a corner or something like causing the limit to not, or the derivative not to exist. But here we're showing specifically it's no, it's the vertical tangent. So that's why I'm going back to the to my limit definition here. Okay, now notice if I try to do direct substitution at this point, it doesn't work, right? So what I'm going to do is multiply the top and bottom by the cube root, or 1 over the cube root. That'll get rid of the 0 in the numerator. Since I'm expecting this to go undefined, I want to have the x left in the denominator here. And I guess we should have, I did want to do this from one direction. I'm just going to pick from the left, I guess. Right. So this would be the same as like when we plug that in, it's undefined. But here I'm not plugging anything in, right? I'm just saying, look, okay, look, the limit's infinite here, which means that it's like, that means vertical. So it's kind of the same thing. Yeah. Is that okay? So again, nice problem because it really kind of forces you to be familiar with the definitions and like what does all this stuff mean, which is often the hardest part of the calculus part, is just like keeping all the definitions straight, and like what kind of stuff is interchangeable, like slope and tangent line and undefined are all kind of related in this case, but not all the way related. Okay. Anybody else happy to do more? Mackenzie? $17? Also from 2.8, right? Okay. Go back over here. I guess as long as I have this all set up, I might as well do the inserts here. Okay. All right. So let's do this. I'll make a graph of e to the x here real quick. Okay. Make this look the way I want it to. All right. So here's my graph of f of x. Yeah, it would be like me equivalent of me typing this into my calculator. I just used a graphing software. It would be easier to get it onto the screen or dumped into OneNote. So if I look at this, I'm going to notice, hey, the slope down at this end is basically 0, right? It's basically horizontal, that's basically horizontal all there. Everybody agree with that? I get to this spot, and the slope is real small and positive, real small and positive, real small and positive, getting a little bit bigger and positive, a little bit bigger. That looks like about a slope of 1 right there. I'm just kind of eyeballing things. And then a little bit bigger and a lot bigger, like pretty steep, super steep, like like getting real steep. So I'm going to just kind of draw this in. So like this whole end, all slope 0 basically, starting to get a little bit positive, little bit positive, little bit positive. We said that this spot here was like 1. And that actually is kind of looks like where it's crossing anyways. And then we're getting a little bit more positive, a little bit more positive, a little bit more positive. What does it kind of look like? The same thing. Yeah, so the guess is for f of x equal e to the x, f inverse of, or f, the derivative of f of x should just be e to the x. That is the case. That is the derivative of e to the x. That's something we would prove in the next chapter. But that's what I would have noticed is like, hey, each of these spots, I'm just kind of like going a little bit, drawing in a tangent line, guessing at the slope number, and it kind of lands where the graph is. Okay? There's nothing really like calculation that I'm going to do here. I'm just kind of guesstimating. Who else has something? Happy to do more. Doesn't have to necessarily even be from 2.7 or 2.8 if you still have old stuff that you need to talk about. Happy to do more. Mia? Okay. Sure. So that's on page 129. Previous. There we go. Okay. So this is 2.5, number 54, right? That's what you wanted? Okay. Grab all these. Oh boy. Go there. Okay. All right, so it says, use the intermediate value theorem to show there is a root of the given equation on the specified interval. So what I'm going to do is when it asks me for a root, that's the same thing as solving the equation equal to 0, right? So I'm going to say, all right, let the function that I'm going to use the intermediate value theorem on be this. The first thing I need to do before I can use the intermediate value theorem is to show that the function I'm working with is continuous over this interval. What's the easiest way to do that? So x squared minus x is a polynomial. Which I know is continuous over its entire domain, which would be everywhere. And sine x is also is a trig function. And I know that's continuous over its entire domain, which again was all real numbers. So I've got then that f has to be continuous, since it's just the sum of continuous pieces, or sum or difference of continuous pieces. Feel okay? Maybe I should say so the sum or difference of continuous pieces is continuous, so that we can say f is continuous. Now what I need to do we need to find some a and b on that interval 1, 2, such that f of a is less than 0 and f of b is bigger than 0. And if we can, I think this is probably or equal to would be also fine. But if we can do that, we're done. We can just quote the intermediate value theorem and then we're finished. So for me, what's going to be the easiest thing to do? I'd probably just look at the picture and pull some x values from the picture. Or I can just plug it to my calculator and try some test values. If I was trying to do this with no calculator, that's a little bit trickier. I'd have to think a little bit harder about how to estimate some values out of there, since the only trig values I know on from 1 to 2 are like radian angle measures, which then are a hassle to do, like the x squared minus x part too. And I guess I would probably prefer not to have to go that route. My assumption would be that this would be a calculator active kind of question, because to compute the values here is just an awful hassle. I'm going to reset my window here on my interval from 1 to 2, since I know that's where I have to pull my x's from. So looks like anything over in this section should be okay. Let's make that a little bit. No, I did my window from 1 to 2 because my interval was from 1 to 2. And then I adjusted the heights to be -2 to +2 when I saw the picture I was getting. So if I do second and trace value, looks like 1.1 should be good. So I'd say that, okay, f of 1.1 is equal to whatever that was, -0.78. and then f of 1.9, somewhere over here, should be good. So that's 0.76-ish. So I can say by the intermediate value theorem, there exists a C on the interval 1, 2 such that f of C is equal to 0. After I showed it was continuous and found something smaller than the desired value and bigger than the desired value, I know there has to be some x that gives me the desired value on that interval. Yes, you can't use the intermediate value theorem without it. So if it says use the intermediate value theorem, it's continuous, but you still need to explain how you know it's continuous. You're welcome. But again, this is not too bad, right? For a proof-ish question, that was pretty quick, pretty easy. Nothing complicated happened. Probably the hardest part was explaining the continuity. But it's just remembering the stuff that's in, by definition, continuous. And then some difference product quotient of continuous is continuous. Even the composition of continuous is continuous. So like as long as you have continuity on a specifically like polynomial and trig pieces are polynomial pieces and like sine and cosine are lovely because their domains are all real numbers anyways. So you don't even have to worry about like multiplication or addition or subtraction or like composition because the domain doesn't matter because the domains are all the same.
Pretty tired, yeah. What are those? Well, you know, when you just like are saying, like, and you just, your head goes down and you're like, oh,
Yeah, it happens to me at night.
it's happening to me right now.
So, as I had said here, I made some more practice multiple choice questions. This is just like a normal homework assignment or whatever. This is not a big deal. The due date I made for the 18th. What is that? Is that Sunday? Yeah, so I think it has the same due date as the problem set. Yeah. They wouldn't let me pick midnight, so I had to pick 11:45 a.m. on the Sunday. Figured that would be the least confusing rather than picking like Monday morning at 12:15 a.m. or something. Feels like somebody's just going to screw that up.
So we gotta get it out.
Yeah, but you have the rest of today. You can start on it. And again, feel free to work with somebody else. You can talk things through. Everybody should submit their own because I don't want to have to worry about like who's working with who and all that. But like you can do it alongside each other. Totally fine. I would encourage you guys that on this one, since the stakes are pretty low, that if there's unless there's a calculator on it, try at least to not do it on your calculator. And if you're like, okay, I think this is the answer, now let me check. Like try to start getting in the habit of doing some of these that way, just so we get used to how to do something without the calculator. Because some of these are pretty easy without the calculator, but you should still, you don't get to use it every time. So getting a little bit of practice here.
Yeah.
Newton didn't need one.
Okay.
That's like he's done.
Newton's smarter than me, so.
That's debatable.
Yeah, actually.
With the amount of accumulated knowledge post his death that you know that he doesn't,
True.
You know, it's arguable that if you transport yourself back into the 1700s, would you be the smartest person there?
So fun.
Yeah, I think
You're the smartest person.
You would probably be executed for heresy though, because even the really unreligious person in 1700s is going to look like a religious zealot to you. Like, think about how much more religious people were 100 years ago versus even like 300 years ago, where you're coming like off of the Spanish Inquisition and stuff. Where like,
Flying from like towns would be so much easier.
Well, also though, like, wasn't that like the
You could just like
the Enlightenment period too? So I guess they weren't that.
No.
they were still massively more religious than you are.
Yeah, probably.
I go to church every Sunday.
That's all possible.
I go to church a lot of times.
I'm just saying.
Like,
And maybe when I say you, I don't mean the specific you. I mean like the royal you, where it's like all of us.
Yeah.
Like, you take the average person, even the average religious person from now, and you drop them back, you know, like 300 years, they're gonna look like not very religious compared to.
Also, if we like took our money